I'm Professor Robert Zimmer, and this is my cybersecurity course. Welcome. You'll see me twice in each topic. Once at the beginning when I'll give you an introductory video like this one, and once in the end when I will run through a problem, a solution of a problem, either programming or mathematics. We are in this together. It's an exploration for both of us, so please feed back to me and I will respond how this course works. This course runs over 6 weeks at a foolish pace, but individual learners can take as long as they want. You can do this much quicker than 6 weeks. You can do this much slower than 6 weeks. It's up to you. You'll be given 5 lessons each week, or what I'm calling a week. The lessons are interactive and AI-based. That means the system will teach you things, but it will also ask you questions to support your learning. And crucially, it will answer your questions. So feel free to say, I don't understand that, or I see that, but what about this? The system will find a way to explain further. That's the power of AI. You can ask anything, you won't be judged. Learn at your own pace without fear or prejudice, no humiliation. Just ask without needing to feel stupid at all. Just ask. As well as the lessons, you will learn through doing a major project. So throughout the course, you will be building up a portfolio, what we call a System Architecture Document, or SAD. We hope the acronym is not prophetic. It should not be a sad thing. It should be a glad thing. If you do the work by week 6, you will have a complete professional-grade security specification. This is a real kind of document that a security consultant would produce. While this is a hypothetical scenario, it's a real solution. It's what the job looks like. That's what we're teaching you to do. So why is cybersecurity important? What is cybersecurity? Why is it important? So let me start by giving you a little story. This is a true story. In 2017, the National Health Service of the UK was brought to its knees. Not by a pandemic that would come 3 years later, but by a piece of software called WannaCry. It encrypted hospital files and demanded a ransom in Bitcoin. Patient data was locked behind a screen that said pay $300. WannaCry exploited a vulnerability that Microsoft had patched 2 months earlier. Unfortunately, the NHS had not applied that patch. The total damage worldwide was estimated at $4 billion. The ransom the attackers actually collected about $140,000. The real cost of this thing is much more than what you pay the ransomers. The real costs of these errors are extraordinary. And here is an uncomfortable truth about this. It's not that hard. The attackers did not need to be brilliant. They needed the defender to be careless. The attacker only needs to find one way in. The defender needs to protect the whole wall, protect everything. That asymmetry is a central problem for cybersecurity, and it is what this course is about. We'll get you there. What is this? So let me tell you a bit more about the course week by week. Over the next 6 weeks, we're going to build up the full picture of how to defend a digital system, layer by layer, threat by threat. Week 1 is about warfare. Well, sort of. We are concentrating on the adversaries, who are the attackers. What do they want? And how do we keep our secrets from them? How do we use mathematics, specifically encryption, and programming to do that? As an example, at the end of the first week, we will crack a code ourselves, following a technique the US used to crack a Soviet code not that long ago. It only works because the Soviets were careless, again like the NHS. We will learn how not to be so careless with our systems. Week 2 is about trust, gone from adversaries to trust. But this isn't warm and cuddly. It's about how we can trust each other while we're strangers without really trusting each other. So how can 2 strangers agree on a secret over the open internet? This is called the key exchange problem. The solution is called public key cryptography. It's one of the most beautiful ideas I know of in computer science, and I'm really looking forward to sharing it with you. We'll also learn in this chapter how TLS works. Well, TLS is the protocol that runs invisibly every time you see a little padlock on your browser. So you'll know what that means. You'll be able to astound your friends with your knowledge of what that little padlock means. Week 3 is where things get ugly. Software bugs, buffer overflows, SQL injection. We'll look at real vulnerable code, break it, and then fix it. That's the solution. Week 4 is about the future, and the future is alarming. Quantum computers threaten to break nearly every public key crypto system we rely on. Not tomorrow, probably, but quite likely within a decade. Intelligence agencies are already hoarding encrypted data today, waiting for a quantum machine to break it. We call this harvest now, decrypt later, and it means a quantum threat is already making itself felt, even though the machine doesn't exist yet. We're getting you ready for the future. That's part of this course. Week 5 takes us to blockchain and distributed ledgers. This is the security behind Bitcoin and all such systems. And it's been used in a lot of other things as well. And here is how we can build a system where we don't rely on anybody trusting anybody else, but the record's still reliable and unchangeable. We'll look at the maths of this. We'll look at hash chains and Merkle trees and smart contracts. And we'll learn how a single bug in a smart contract once cost $60 million in 7 minutes. Week 6, the final week, is about the human side of things. Social engineering, phishing, biometrics, privacy law. The most expensive fireworks in the world, firewall in the world, is useless if someone can talk the receptionist into holding the door open. We end where all security ends, with people. Okay. As well as what we've got on our screens, we've got a textbook. Our core textbook is Ross Anderson's Security Engineering. It's a standard reference in the field, or at least one of the standard references in the field. It is comprehensive, and unusually for a textbook, it is genuinely well written. Even more unusually, it is available legally for free on the author's website. I will point you to the specific chapters each week, but I've downloaded them in case it disappears. Read them, they're worth your time. We only can cover a small percentage of the chapters. Read the other ones too. It's a fantastic book. We're really grateful for Professor Anderson for making it available to us. Okay, now to the final word about the course design. This is a just-in-time approach to technical material. I will not front-load you with abstract maths and then eventually get around to explaining why it matters. Instead, we start with problems. How do we keep these documents secret? And we introduce the maths only when we need it to solve the problem. You don't need to be a mathematician. You don't need to be a fantastic programmer. You need to be somewhat adept in maths and programming. You need to be curious. You need to be willing to think like an attacker. And you need to be comfortable with the idea that in the end, there are no perfect answers to security. Nothing's perfectly safe. There's only trade-offs. We'll learn about those trade-offs in week 1. We want to find the best solution by trading off availability and security. As I said, you'll see me each week, once at the end, and once at the beginning, once at the end. And these videos are designed to bookend the lessons and give you something concrete to anchor the week's material. But the lesson to take away for now, going back to that NHS story, the NHS did not lose out to a genius and lost out to a 2-month-old patch it hadn't applied. That's the kind of failure this course is designed to prevent. Security is not about paranoia. It is about discipline, clear thinking, and understanding the adversary. By the end of these 6 weeks, you'll have the understanding and be able to prove it in the real world. Okay, so let's get to that, and I'll see you in the beginning of week 1. Bye for now.